I used to live in Maryland. Oh, right. I was in Columbia. I was at NASA. It's nice.
So here, very tall, block people.
Have you on the phone? I know. Okay, it's pretty much just gone 8, so I think we can, and nearly all the seats are taken. So let me begin. I'm Ben Dorman, I'm the chair of the Friends of the DAO, and I'm starting off by acknowledging that we're on the land of the Senchothan-speaking peoples, the Coast Salish nations. Tonight's talk is being given by Max Kurzner, who's a graduate student at the University of Victoria, and he's just given me a confession that he is not from the other center of the University, New York City. He actually grew up in Connecticut, although he may be born there. So, but Max graduated from Colgate in Upstate New York and Tufts, and then came here, which was a thoroughly good move. Max is going to tell us all about the shapes and sizes of galaxies. Why are there so many different kinds of galaxies and why they look like what they do? And so without further ado, I'm going to pass this microphone to him. This is actually necessary, even in this small room, because the people out there in the rest of the universe have to hear us somehow. So here's Max Kurzner.
All right, thank you very much. So hi everyone here and in the universe online. It's nice to be with you all this evening. As mentioned in that lovely intro, thank you. I'll be talking tonight about how galaxies shape up, why we have such a wonderful and wide variety of galaxies in the universe, what galaxies even are, and what we can learn about our own Milky Way through the study of galaxies. So without any further ado, this here, hopefully might be recognized to some people, this is a view of our own Milky Way galaxy. This is an image taken in Grand Teton in Wyoming. Take this image, but I wish I did. And what I'm hoping this image evokes is a sense of place in the universe, in the sense that we are here somewhere special and that we are part of something larger than ourselves. Also, hopefully by the end of this talk, you'll be able to look at this and be like, oh yeah, Max, that shows that we live in a spiral galaxy, because how the stars are distributed in this image, the fact that we see these dark blue, purples, and black bands in the sky shows us a lot about the Milky Way, which is our home, and we can learn a lot about how it formed, what's going on with it today, what will be happening with it in the future, as well as what will happen to other galaxies just like our own throughout the universe. But first, we're going back to school. Just kidding. We have some basic terms that I'm going to refer to a lot in this talk that hopefully I can explain in a way that is not too much jargon for us to learn this evening. So while this talk is on galaxies, we first have to know what stars are, as without stars, there would be no galaxies to speak of. So stars, at their most basic, are regions of space that have condensed down to be so dense and hot that they can actually fuse hydrogen into helium. They are basically giant nuclear fusion reactions that turn hydrogen into helium, and I will not talk about that extensively in this talk, but just to ground us here are 3 very famous stars in our galaxy, and Sirius, Betelgeuse, and Procyon. These form the winter triangle asterism, and the reason I included these in this image is I wanted to make a point that stars can be blue, they can be orange and red based on their temperature and also how old they are. Something that affects the color and properties of galaxies are the properties of their stars. So understanding that stars can form in different ways and live different lives is a way that we can understand more about the galaxies themselves. So this is a bit of a loaded term here, but what is a galaxy? We'll get into this in vivid detail, but at its most basic, a galaxy, like pictured here, is just a gravitationally bound system of stars, gas, dust, planets, people, in our case, in our galaxy, all in one region of space. They can vary in size from the size of the Milky Way to many times smaller than the Milky Way, than we'll see, to even larger. But really, in terms of the universe, they are the most fundamental large-scale structure that is held together by gravity. This doesn't mean that the galaxies will always look like this. They do change and evolve throughout time, but at its most basic, a galaxy is just stuff held together by gravity. A term I just mentioned you would have heard is gas. So I'm not talking about gasoline in this case. I'm talking about hydrogen. This image here shows the Orion Nebula, where you can see some of the stars like Rigel and Betelgeuse up there. But you can see this lovely pink and reddish colored regions. Those are actually hydrogen gas that are reflecting some of the starlight from these very hot and young stars that are forming in this nebula. So gas is the fuel of star formation in galaxies, and this is what allows stars to form, as you need gas to condense down to make stars. Without any gas, just like about a car, you won't be going anywhere and you won't be forming stars, and this actually will change a lot about your galaxy. The next term is dust. It's kind of a mysterious term there, but this is dust in the cosmic context. So this is Barnard 68. Sam Fielder, who gave the star talk a few weeks ago, told me he used the same image, so apologies if you've already seen this. But what dust is kind of everything else in a galaxy. It's the more complex chemistry and some heavier elements in more dense, cooler regions where it looks like there's nothing, but actually this is just material that we can't see through because of the radiation, the wavelengths that our eyes can see at. But in a region like this, you can have stars form, you can have complex chemistry, things that lead to planets and very interesting stuff. But in terms of galaxies, when we talk about dust, we see these beautiful dust lanes. So this galaxy here, you can see these blue and pinkish and reddish regions where stars are forming, but the next generations of stars are forming in these dark dust regions, which we can't see with the naked eye, but looking at other parts of the electromagnetic spectrum, astronomers can actually study stars in their very infant years. The final term and the basics that I'll be talking about is dark matter. So without dark matter, we would not actually have galaxy formation on large scales. What dark matter is somewhat mysterious, and there are people who devote their whole careers to it. But for people in the galaxies, what we know is that there is matter out in the universe that we can't see with our eyes. It doesn't interact with electromagnetic radiation, but it exists, as we can infer. It's there due to its gravitational influence on surrounding material. So in this case, we have a galaxy like our own Milky Way, which has a disk and a very dense central bulge region, but this tenuous blue sphere around it is what's known as a dark matter halo. And everything within this larger region compromises the galaxy's sphere of influence, so to speak, the gravitationally bound region that is distinct and from the rest of the universe insofar that things in here are associated with this galaxy either falling in, coming out, or just rotating around it. But dark matter holds us all together in a way that normal matter cannot. Before we jump into the rest of the talk, I just want to talk about why galaxies are important and where they fit into the scheme of how we understand the universe. So this is the entire universe right here. As you can see, it fits on one PowerPoint slide conveniently. When we talk about how things have formed in the universe, we start here at the beginning, the Big Bang, and eventually material just formed as the universe expanded. You have things that like stars, planets, and galaxies form over the course of many billions of years. We live about 14 billion years after this beginning of the universe happened. We'll not be able to debate philosophically what that means exactly, but we can just talk about this as a starting point, and our interest in the talk will be kind of mostly in this region where we go from having nothing to having something and complicated things like galaxies that can exist at all. Also, I meant to say, if you have any questions throughout the talk, feel free to raise your hand, or if you have any burning questions, but I'll leave plenty of time at the end to take questions as well. So just to get out of the way. going back to this question of what is a galaxy, it was a little tongue-in-cheek of me to just say that it's gravitationally bound and leave it there. You could quite literally write a whole PhD thesis on what a galaxy is and probably still have more to uncover. They're incredibly complicated, and we're just going to scratch the surface tonight. But luckily, with the advent of advanced supercomputers, you can actually make a galaxy and make a YouTube video of it. So what this video is here is a simulation of a galaxy like our own Milky Way forming from the beginning of the universe till today, where the main panel here is just showing the gas and dust and material falling into the galaxy. And up here you can see a scale bar for size. The Milky Way is about 100,000 light years across today. A light year, quite literally, is an astronomically large distance that is impossible to comprehend. But for our purposes, 100,000 is the size of our galaxy, and that'll be kind of our measuring stick for the rest of the evening. The bottom panel here shows what we know as the cosmic web and these filamentary structures where material on much larger scales falls into the galaxy and is also pushed out by energetic events such as supernovae and things which I won't talk about in this talk, but allow the galaxy to change over time. Convenient camera switch to show the structure of the galaxy, how as material falls into it, it kind of flattens out into a pancake. If you ever taken a physics class, you've heard the example of a figure skater pulling their arms in, and as they do, they speed up due to what's known as the conservation of angular momentum. Same thing happens with galaxies. When you have material that's falling in that has some general spin in a direction, you'll end up with some sort of flattish disk of a galaxy, which we call a spiral galaxy. The final thing I was pointing out here is you can see the gas as well as the dark matter distribution of the galaxy itself, showing that these map to the same region. But for our purposes, this is just showing that we can understand how galaxies form through our own observations, but through numerical simulations as well. And I want you to keep this simulation in the back of your mind in the rest of the talk, as you'll see some differences between this and theory, as well as things we are still learning today. So as promised, you can't talk about the shapes of galaxies without showing some different types of galaxies. So far, we've really talked about spiral galaxies mostly. So things like that look like our Milky Way. This is NGC 4404 for those keeping track at home. This galaxy is about the same size as the Milky Way, and it's noted for being very blue in color. The reason for this is that it is still actively forming stars. And when you're forming stars, the youngest stars are the bluest and hottest. They live fast and they die young. So if you're not forming stars, you will not see as much of a blue color in your galaxy, which is evident when you look at elliptical galaxies, which are redder or orange in color. They're very large and you say looking because they are usually the result of mergers of massive galaxies like our own Milky Way, which we'll talk about shortly. And the reason they look somewhat spherical in shape is that you take these nice symmetric spiral galaxies, smash them together, and over the course of many millions of years, the orbits get all tangled up, and what you're left with is basically a ball of stars, which are no longer forming stars as there's not much gas or material left for them to do so. But that's all well and good, and we could end the talk here and we would be none the wiser, but what do we do about these guys? This is not to toot my own horn, picture from some of my own research. This is what's known as an ultra-faint dwarf galaxy. This little green, I guess, nugget, for lack of a better word, is teeny tiny. You can fit thousands of these in our own Milky Way. And you might say, Max, that's just a smudge on the camera lens. I can assure you it's not. This is a real thing. But this is a galaxy that, unlike our own Milky Way, is very small. It is bound together by dark matter and gravity. But we don't understand, at least at this point in the talk, how something like this can coexist with these galaxies in our universe. So hopefully we'll walk through some terms that help us understand why we have galaxies in such a wide variety of shapes and sizes in the universe at all. And that brings me to the maybe more high level, why do we care slide. So we should care about galaxies as we do live in one, while our day-to-day lives are not really affected by the Milky Way in terms of understanding our place in the cosmos and the past, present, and future of our own Earth, solar system, and everything in our galaxy, it's imperative that we learn more about the Milky Way and the galaxies around us. Not only this, we can, as I mentioned, we learn all about the different time frames that we are interested in. For the physicists in the room, which I guess I am among many, these are important laboratories. They can study physics on basically every scale, from chemistry involving how light is emitted from atoms and how material forms in dust to make more complicated molecules, all the way up to gravity on its largest scales and whether or not our own theories of how mass can even self-gravitate can be tested by studying galaxies. And then also, it's like anything in science, it's really interesting. And I'm of the opinion that if something inspires joy and makes you happy and just wants you to learn more, then you should keep doing that. In a society like our own, where we encourage people to study science and to push the envelope, the study of galaxies checks all those boxes. And you can trust me on that, as I am a cool guy. Time for some more basic terminology, because at this point, I haven't told you how we know any of this yet, which is a fair point. So to begin with, when we talk about light, we're talking about what's known as the electromagnetic spectrum, where you can see this little small region here between 400 and 700 nanometers is what's known as visible light. This is the light that we can see with our own eyes. And astronomers can build telescopes in space, on Earth, right here up the parking lot, to study the different parts of the electromagnetic spectrum. And I'll show that in a little how we do that. But every different part of electromagnetic spectrum, from very highly energetic radiation to low energy radiation, tells us something different about a galaxy. You can also do what's known as spectroscopy, where you can, this is a nice little graphic from the WST team, where you can take light from a distant star or galaxy, and you can split it up with basically like a prism into its components, and you can see the fingerprint of every unique element or molecule in that light. So for instance, here is a spectrum where you can see carbon, nitrogen, oxygen, and iron. So I couldn't see that there. And what this tells you is how much of that material is in that sample, and that tells you about the physical processes happening in that galaxy or star or astronomical object of interest. So spectroscopy is really important, but bringing it all together, if you study across the entire electromagnetic spectrum, where you see this is the Whirlpool galaxy, a very famous spiral galaxy. So with our eyes, we see this. We see stars like our own sun, and we see that it is forming stars just like our own Milky Way. If we look at really cold gas in the radio, which is low energy, you can see some of the cool gas that will one day form new stars, and you can see is hidden in these dust lanes. Looking in the infrared, we see things slightly cooler, and going to higher and more energetic wavelengths, you can see more high energy and exotic physical processes, such as very young and hot stars, as well as X-rays from the center of the galaxy and other galaxies in the nearby region. So we can put together all this information in what is known as multi-messenger astronomy, where we can understand quite literally the entire electromagnetic spectrum for every object we can learn about, and that tells us the full picture of what's going on there. Bring it back closer to home again. Here are a couple galaxies that live in our neighborhood. So this is us. This is the Milky Way here, about 100,000 light years across. Our closest big neighbor, the Andromeda galaxy here, is slightly larger than the Milky Way, and it's about 2 million light years away. We'll talk about that more in a second. But you can see we have some peculiar dwarf galaxies in our own neighborhood here, like the Large and Small Magellanic Clouds. Unfortunately, these galaxies are not visible in the northern hemisphere, though I'm told they're quite stunning to see. You can see them with the naked eye in the southern hemisphere. And we also have some other small galaxies that seem to coexist with our own Milky Way. So clearly, when we have large galaxies, small galaxies seem to be in tow. And that is a theme when we look throughout the entire universe. What this tells us about broadly in terms of galaxy formation evolution is that in the schematic here, to get a really big galaxy, you need to have a lot of small galaxies generally. And you can think about this tree diagram here in terms of time. So you have earlier in the universe some smaller galaxies that over time coalesce and merge with each other and eventually built up to something like our own Milky Way. In the middle of that process, you'll get pictures like this, which are quite stunning. These are known as the antennae galaxies. These are two galaxies like our own Milky Way that are in the process of undergoing a merger, where over the course of many millions of years, due to their own mutual gravity, they are essentially colliding with one another and forming a new galaxy. And this, you can imagine, is a quite chaotic and violent process that will dramatically change not only the shape of the galaxy, but also the processes and properties of itself. So you can kind of see here that there was a galaxy here, not really longer. This one here is kind of being bridged into the one here, but what's happening is triggering some very active star formation region. And while this is not the case for all galaxies, galaxies can just grow by themselves without mergers. The way that you really move the needle with galaxy evolution is through mergers of galaxies in the universe. It wouldn't be a talk in 2023 without another JWST image. This was one of the first images released by JWST last summer. This is known as Stephan's Quintet. And you can count 1, 2, 3, 4, 5 galaxies here, of which only 3 are actually interacting. But this is a wonderful view of the really beautiful and chaotic picture of galaxy mergers and evolution in our universe. You can see this wonderful tail here from this galaxy and how these shapes of these galaxies are being quite dramatically altered, and that star formation is being triggered at large degrees by this process. And that this is in the near infrared lets us learn about different types of stars that we wouldn't be able to see about in our own eyes. You may note that this galaxy looks kind of strange. That's because since we're looking in infrared, we could peer behind some of the dust that would otherwise be blocking the way there. So this brings us to what looks like a very boring plot, but this is probably one of the most important relations in all of galactic astronomy, which is what's known as the star-forming main sequence of galaxies. We have essentially galaxies that form a lot of stars, but aren't as big. But when you have really large, massive elliptical galaxies, they generally don't form stars. They're redder in color, and they're not as blue as galaxies like our own Milky Way. That works all well and good, but that's not everything in the universe. So what do we do about the rest of the galaxies, and do they fit into this picture? This brings us to the dwarf galaxies, which I talked about a little bit before. In some sense, they are just kind of the cosmic leftovers, at least in the smallest scales. This is a view of the Milky Way halo again, where all these little white circles are dwarf galaxies that are in our so-called sphere of influence. You can see the names here. Most of them are named from the constellation that they are in the direction of in the night sky. And the ones we talked about so far, we have the Large and Small Magellanic Cloud, which are only visible in the southern hemisphere, but that doesn't make them not interesting to study. These things are really interesting as the smallest systems are actually relics and fossils, just like the dinosaurs would be on Earth. When you uncover an ultra-faint dwarf galaxy, you're actually looking at a system that has not changed or formed stars since the really beginning of the universe. So they're a unique opportunity to study the early universe without having to peer far away in your telescopes. But in a less extreme example, you can see, the Andromeda Galaxy, which is the closest galaxy to our own that is a spiral galaxy. It has quite a few companions in tow, such as this dwarf elliptical galaxy. So sometimes you have galaxies that are just smaller than the ones that we live in, that are relatively normal, so to speak, and bridge the way between these faint blobs that are only a couple hundred or 1,000 stars, all the way up to galaxies like our own Milky Way. Not only do these systems show what the universe was like in the early universe, they actually show evidence of interacting with our galaxy and galaxies like it today. This here is showing a very famous dwarf galaxy stream known as Sagittarius, where you can see evidence of it, the fact that has relatively recently, in the past only a few billion years or so, fallen into our own galaxy. And this is not just a unique situation for one dwarf galaxy. These colored streams here indicate streams of stars that astronomers have identified as belonging to dwarf galaxies that have either been gobbled up long ago or in the process of falling into our galaxy. So these small galaxies, since they're some of the smallest gravitationally bound systems in our universe that are galaxies at all, when they interact with our Milky Way, they can be some of the building blocks with which you build a larger galaxy without completely destroying the system, but they also leave a unique astronomical fingerprint when you are looking at the galaxy itself. So we can look at our Milky Way, look at all the stars, and study some stars that actually originated their lives outside of our own galaxy. So dwarf galaxies are a great tool for understanding more about the history of galaxies and what their interactions were long in the past. Excuse me. That brings us to galaxies in extreme environments. So the galaxies like the Milky Way live on their own, so to speak. They don't have many neighbors. This here is a picture of the Virgo cluster, which I study as part of my PhD thesis. These black circles here are not Planet X. They're just masks of foreground stars. But one thing I want to note for this image is that extreme interactions of gravity, where you have many thousands of galaxies in a cosmic volume that is generally only full of a couple galaxies in the case of the Milky Way, can influence how galaxies grow and change in unique ways that make them great laboratories for studying how galaxies form and change. One thing you may have noticed so far is that there's a lot of red and orange galaxies here. This guy right here is M87. If you saw on the door on the way in, that is the galaxy that had its black hole image a few years ago. It is one of the most massive galaxies in our local universe. It's a couple million light years away, so that black hole will not impact us anytime soon. But this, along with the two other main elliptical galaxies in the cluster, really influence and bully the other galaxies. It's very mean. But as a galaxy falls into the gravitational influence of this cluster, it gets its material taken away from it. It interacts with galaxies and merges quite rapidly. And as things fall towards the center, generally they're not going to be forming stars anymore. The great thing about studying galaxies in clusters is another image here. This is a SMAC 723 cluster. You can understand far away objects essentially for free because of gravity. So you can see these weird kind of arcs here. These are galaxies far in the distant universe that, due to an intervening cluster of galaxies, the gravity is actually warping the light and bending it towards Earth in a way that we can actually study things really far away without having to look as far in the universe with our telescope. And what this tells us is that these large cluster environments are the end-all, be-all for the large-scale structure of our universe. So galaxies will live in things larger than ourselves. The Milky Way is part of a much larger group of galaxies, which we'll talk about quickly at the end of this talk, but that ultimately the shapes and sizes of galaxies are dominated by gravity, and the extreme end really changes things the most. That brings us to the early universe, which I talked about briefly. You can learn about the early universe not just from gravitational lenses. You can just look in the sky for a long time and look really far away and either get lucky or build a nice telescope. So this little guy here is what's known as GNZ11. It was the furthest galaxy ever discovered with the Hubble Space Telescope. It was formed about only 400 million years after the Big Bang, which I know I'm throwing the word million and billion out a lot, kind of like that means it nothing. But to put things in perspective, this was about 13.4 billion years ago. So while 400 million years is a long time for us as humans, this was essentially in the infancy of our universe. So things were quite different then. So this is really exciting to study galaxies then. Excuse me. And you would say that, okay, in the early universe, galaxies are kind of these weird little amorphous blobs. Fair enough. When we look only 5 to 7 or so billion years ago, you see in the same picture. You have some galaxies that are kind of blobs. We don't really have much structure at all, but that really isn't the full story. Is this thing on? Great. Right, so this was saying that these numbers here, or what's known as redshift, just tell us how far things away are. These things are only halfway across the universe. I use only very much in quotations, but you see the early universe, you think these galaxies are kind of just blobs because these blobs haven't had time to form into cool structures and that they have not had time to merge with galaxies yet, right? Wrong. With the JWST and the next generation of survey telescopes, we're actually seeing a lot more structure and a lot more complicated looking galaxies in the early universe than our models would have predicted, which is really exciting actually, because it gives people like me a job, as otherwise us grad students would be on the street. So these mosaic here to show some of the exciting galaxies that have been identified by JPST. And what you're seeing is, you can see this guy here is like, kind of looks like it has a disk, like a spiral galaxy, or even some sort of complicated mergers in the relatively early universe. So clearly galaxies are forming much more rapidly than we would have originally thought. And galaxy formation is a faster and more complicated process in the early universe than we would have initially thought before we put these telescopes in space and built larger telescopes here on Earth. So that was a little bit of a whirlwind. Wouldn't it be mistaken to think that this doesn't really connect to our Milky Way? So here we are again in the Orion Spur, about 3/4 of the way out in the suburbs of our own Milky Way galaxy. So as it is, we've learned so far that galaxies grow, they change, they evolve. But what does that mean for us here at home? What it means is a future in a new galaxy, which astronomers have dubbed Milky Way. This is the Andromeda Galaxy again. This is not a real image, but in only a few billion years, since Andromeda is only 2 million light years away, it will race towards our own galaxy and actually merge with our own. By then, the sun will probably have died out, and the room won't be here. Excuse me. Dust. Sorry, folks. What I was saying here is that we will have a merger with the Andromeda Galaxy in only a short few billion years, and we will become part of a larger elliptical galaxy, like is the fate for basically all large galaxies in our universe. But that's not the full story, as I said. We're in a spoilers. We're in a group of galaxies known as a local galactic group, but we are part of something much larger than ourselves, even within the galaxy. We're part of known as the Virgo supercluster, which has many thousands of galaxies in a larger region of space. Well, we can zoom out from here even further, and the largest structure in the universe that we say we belong to is known as the Laniakea supercluster, which is many thousands and millions of galaxies like our Milky Way, all shapes and sizes. And our future is to be a galaxy in this group and this cluster, where we will grow and change along with all the other galaxies that are here in the universe. Oh, thank you. And bringing it really back home, you can see this lovely image of the Milky Way here in Victoria. I hope that you can now confidently tell your friends and family when you see a view like this, that yeah, this is a spiral galaxy. This is the Milky Way. This is home. And we are a galaxy like many in the universe, and our future is exciting as well as chaotic, but also we've learned a lot about where we come from and where we are now. And I personally, when I look at something like this, feel very grounded and feel very privileged to be able to study galaxies in such a wonderful place. So thank you very much for your attention. I would be happy to take any of your questions, and if you're interested, you can get in touch with me at these links. Thank you.
Questions? So my understanding is that all the quote unquote normal galaxies have a giant black hole in the center. Is that similar for dwarf galaxies, or do we know?
So that's a really good question. I'm not sure if you could hear that online, but the question was, all normal galaxies in the universe have a black hole in the center, and does that apply to dwarf galaxies? The answer is we don't know yet, but there are people who study what are known as dwarf active electric nuclei, and there is evidence that some of them do have black holes, but not all dwarf galaxies, especially the ones that are really small and faint.
Any other questions? Okay, well, thank you very much, Max. That was spectacular, and the pictures are amazing. And yes, that's the best. And we expect to see much more going forward. Thank you.